in the last video, we talked about this diagram. This is really the perceptron architecture. I simplified the diagram a little bit here to really simplify the math. So we have the input value. We refer to this input value as house size as an example. And we want to determine the house price or to predict the house price. So y hat is the predicted value. And we'll always have some bias with input value 1. And B, of course, is a constant to determine during training. So during training, we need to find B and W. So basically, we train this perceptron to zoom in on the best value of B and best value of W that represents the best relationship between y hat and the input. So the perceptron does a dot product. So it multiplies the weight by the input value X, and then it adds the bias B times 1, which is B. And it applies some activation function. I gave examples in the last video, like a sine function, for example, to give us the non-linear fit for the data, because the data may not be linear. So this part is linear, this part is non-linear. So typically we always have to do training first to find the values of B and W that represent the best fit, that give us the best predicted value to an input value. So B and W are unknown, while X and Y are known at training time. So basically, we have a set of data, input data, and corresponding output data. We run the training process on this perceptron iteratively, repeatedly, until we find the best value of B, the bias, and W, the weight, that will give us the best relationship between the output and the input. Once the values of B and W are determined from the training, then basically you deploy this perceptron in production to do inference, which means to predict the value of the output given an input value. So at inference, the bias and W, the weight, are known, fixed. And the model has to infer the predicted output for a given input X. Now, let's go into a little bit of depth into the training process. We initially select a random value for the bias and for the weight, because we really don't know. We have no idea what the bias and the weight should be. So we randomly select a value for the bias and the weight. We have the bias, we have the weight, we have the input value, then we calculate y hat, which is W times X plus B. And then we calculate the cost. So the cost really tells us how the predicted value is off from the ground truth, the actual output. You have to compare, because we have the output in this training data set, we have the input value and we have the output value. So we compare the predicted value y hat to y, which is the ground truth. One way to calculate this cost is shown in this formula, which is really, it may look overwhelming, but it's not. So y sub n is actually the ground truth for one output value, because we may have, and actually we always have a large data set for input and output during training. So this is a value for one sample. So a sample is an input and corresponding output. So we have the output, the actual output for a given input. We subtract that from the ground, from the predicted value y hat, just like shown here. Again, x sub n is the corresponding input for this output, and then we add the bias. So we subtract and then we square the resulting value, and this is for one sample. And then we add this error squared for all the samples in the data set. That's what the sum is. Basically, we are adding over all the samples in the training data set, and then we divide by the number of samples. So if we have 1,000 coordinates, x, y, input and output in the data set, if we have 1,000 pairs, n is 1,000. So we sum the error squared, we divide by the number of samples. This is one way to calculate the cost. Here is an example. Let's just assume x has two values, 1 and 2, y has 3 and 4. So 3, the value 3 corresponds to x1, and the value 4 of y corresponds to value 2 of x. And the bias is 1, randomly initialized to 1, and the weight is randomly initialized to 2. We calculate the cost following this formula. The cost is 0.5. We want to drive the cost to the minimum possible, the minimum value, which means the predicted value is really close to the actual value in the training data set. So we want to drive the cost to the minimum, as close to zero as possible. So then we ask this question, are we done with training? Which means, do we have a minimum value of cost? If yes, the training is done. We have identified at this point the right value of the bias and the right value of the weight that will give us the best relationship between y hat and the input. If training is not done, then we have to update the bias and the weight in a way to drive the cost down closer to zero. And then we loop again, we repeat. So we have a new value for the bias, a new value for the weight. Then we have to calculate the y hat, calculate the cost, and then ask the question again, are we done or not? We keep looping, repeating this process until we are done with the training. These steps done in the training process together are called epoch. So whatever we are doing here, we're calculating the y hat, calculating the cost, asking the question if we are done with the training. These are these steps together are called epoch. And we can have multiple epoch. We may fix the number of epoch, or we may do other things to drive the cost to an acceptable value so that we have the best values for B and W that would give us the best relationship between y hat and the input.